Hello. In this video, I'm going to be evaluating two limits from section 14.2 of James Stewart's Calculus Early Transcendentals, 9th edition. And the two limits are these. So first, from problem set 5 to 12, we want to find this limit here, which is number 8. And from problem set 31 through 34, we're going to use the squeeze theorem to find this limit right here. So before I start evaluating these limits, I should mention that in general, there's not going to be one single strategy that works for every limit that you might encounter. Sometimes the ideas that you use for one limit, like the ones we'll see for these, don't really carry over to another limits, and so we'll need to come up with another strategy. But that's okay, because with enough patience and just enough tries at whatever comes to mind, usually the solution kind of makes itself apparent, and then we're able to solve the problem. And we'll see this with this limit right here. So, okay, how do we evaluate this? Well, one thing we can try is, okay, we have this function, and we're taking the limit as xy goes to 2 comma negative 1. And to save ourselves a lot of effort, one thing we could try, as with any limit, is just plug in. So I'll write this in green. And you know what? Let me write this over here. So we're going to try plugging in first. And when we do this, we get, just give me one sec to copy the limits. We're going to get, just plugging in 2 for x and y for negative 1. We're going to get 2 squared times negative 1 plus 2 times negative 1 squared, all over 2 squared minus negative 1 squared. And this in turn, okay, so the denominator is going to be 4 minus 1. And that's already promising because we know this is non-zero. So our hope is that this already kind of gives us the answer that we want, because it looks like this function is going to be continuous at this point. And the numerator becomes, well, negative 4 plus 2. And when we simplify everything, this will be negative 2 all over 3, which, if you want, just pull out that negative and make it look clean. And notice how immediately we got the answer that we want. And importantly, this saves us a lot of efforts from what was my first idea originally when I first saw this problem, which is to note, and I'll write this in blue, was to note that the numerator and the denominator can be factored. So the numerator can be factored as xy times x plus y, and the denominator as x minus y, x plus y. And so when we cancel these factors, we get xy all over x minus y. And indeed, when we plug in our limits to this expression, xy squared all over x squared minus y squared, we established right now that this is just the limits of xy over x minus y. And when we plug this in, we get 2 times negative 1 all over 2 minus negative 1, which indeed works out to be the exact same answer. So this is perfectly fine, but notice how much easier it was for us to just plug in the limit directly, so that we didn't have to use this, we didn't have to see this idea of factoring the numerator and denominator. And that's not to say that in other problems that might be useful. It absolutely could. It's just, if you can see like a more basic easy solution, it's probably a good idea just to stick with that one. And here, the easiest possible thing you can do is just plug in your points into your expression. Okay, but now this leads us to this other problem. And remember how I mentioned that certain ideas or techniques from one problem might not carry over to another problem? We can see that to be the case here because, well, note first that there's no immediate way to factor the denominator. And, well, just already that, it kind of poses an issue for us. Now, one thing we could try is the more basic strategy of just plugging in the limits. That was the easy solution we had in this previous problem. And that gave us the answer pretty readily. So we can try that here. Let's see what happens. We already ran into an issue because that denominator is going to be 0. And so we get this indeterminate form, 0 over 0. So plugging in isn't going to work. We're going to need to be a bit more clever or use an alternate idea. And, well, they kind of give us the thing we should use here. We need to use the squeeze theorem somehow. Now, I'm going to write out the inequalities I used for this problem. And I don't claim that this is the only way you can attack this limit using the squeeze theorem. And I won't try to explain how I got this inequality, and it's going to feel like it's out of left field, but it should be noted that this inequality that I'm using for the squeeze theorem, I just found it after trying out different ideas until I stumbled into one that worked. It's a bunch of trial and error for a lot of these problems. Oftentimes in the solutions manual for a book, you'll see the solution, and it's like, oh, that's really clever. How did they think of that? But what many authors omit, just for the sake of readability, are all of the failed attempts, all of the other ideas that didn't work, that were towards finding the solution to the problem. Okay? So if what I'm going to write feels out of left field, please don't feel discouraged. With enough patience and just trying different ideas that come your way, the thing that I found might come to you as well, or maybe something original, something different, But anyway, okay. So what's the inequality I used? So first, I notice, okay, I'm taking the absolute value of this. And when I do, I can simplify this as absolute x y to the fourth all over x to the fourth plus y to the fourth. Or you know what? Let's take this step by step. So first, the absolute value, we can just do the absolute value of the dividend and divisor separately. I think that's the word for the top, the dividend. I forgot. And, well, noting that the bottom is positive, this is just x to the fourth plus y to the fourth. Again, because x to the fourth plus y to the fourth is always at least 0. And the numerator, by multiplicativity of the absolute value, will be absolute x times absolute y to the fourth. And again, this term right here is positive, so this is just absolute x y to the fourth all over x to the fourth plus y to the fourth. All right. Now we make an observation. Since x to the fourth is always at least 0, because that exponent is even, we have x to the fourth plus y to the fourth is at least y to the fourth. So by taking reciprocals, we get this inequality here. This gives that absolute x y to the fourth all over x to the fourth plus y to the fourth is at most x y to the fourth all over y to the fourth. And what do you know? These y to the fourths cancel for us, and we're left with absolute x So from our previous work, we have this inequality here. Xy to the fourth all over x to the fourth plus y to the fourth is at most x. Now, we can rewrite this inequality to get rid of this absolute value here. Or even better, I'll write it this way. Equivalently, as in what I'm going to write next is saying the same thing as this inequality here. We have this bound here. And now to finish things up, I claim that we can apply the squeeze theorem to this inequality here. But let me remind us of what that theorem says before I do so. So I'll write it over here. Squeeze theorem. So suppose f of xy is at least g of xy is at least h of xy, and the limits of f and h exist and are equal. And let's call the common value of their limits L. Then the squeeze theorem tells us that the limits as xy goes to ab of g of xy, the middle function here, also exists. And moreover, this limit has to equal L. So that's the squeeze theorem. And okay, how are we going to apply it here? Well, scrolling back up, let me remind us that we're taking the limits as xy goes to 0, 0. And we can notice that the limits of the left side and the right side are both 0 as our point xy goes to 0, 0. So since limit negative absolute x equals negative 0 equals 0, and the limits of xy goes to 0, 0 of absolute x equals 0, the limits are equal. If you want to be precise, you could write the limits exist and are equal. So then by the squeeze theorem, the limit of our middle function, xy to the fourth all over x to the fourth plus y to the fourth. Let me clean this up, actually. So by the squeeze theorem, the limit of our middle function exists and equals 4. Or equals 0, sorry. I read the exponents and I said 4 by accident. So let me recap this example because this one's probably like the more important one to like take some notes on. So what are the key takeaways? Okay. So we found already that direct substitution fails, and that's okay. Sometimes it won't work. And if we want to be clear, we can say because, just writing this as my function, f of xy is discontinuous at 0, 0, because it's not defined there, as we found right here. So next key idea for me was to take the absolute value of this and then just clean up things a bit so I get this nice expression. And let me clean up this 4. I am so sorry. X to the 4th and y to the 4th. And the key thing to notice for this solution is that this denominator here is at least y to the 4th, because x to the 4th is always positive. So when you take reciprocals, you get this bound right here. And by using this bound, you can kill off the y to the 4ths and be left with something whose limit is easy to compute. Once we have this inequality, we just rewrite it by getting rid of this absolute value. So for your notes, what I'm using here is that we have this inequality if and only if negative b less than or equal to a less than or equal to b, assuming, of course, that b is at least 0. Otherwise, this inequality actually doesn't have any solutions. Once we rewrite it as such, we already noted that the left side and right sides have limits that are easy to calculate. They're just 0 in each. And so, because we are squeezing this function in between these two, and these two have the same limit as we approach 0, 0, the middle function must also have limit 0 as we approach 0, 0, by the squeeze theorem, of course. Okay. That's it for this video. If there are any questions, please feel free to leave a comment. Otherwise, I'll see you all in the next video.